Hi, and welcome to my talk about how to rangify your code. My name is Tina Ulbrich. I work for the Rosen Technology and Research Center. So what qualifies me to give this talk? In my company, we use the new C++ standards right away, which means we're among the first people who bring the new features into production code. But that also means that there's not a lot of material available to look up how these features are used. In the beginning, blog posts and talks are very technical and focus on how the features were implemented into the standard library. Examples tend to be simple. My goal is to provide more complex examples. Some of them are modified examples from our code base. Before I start, I want to recommend some talks or YouTube videos to you that you can watch if you want to learn more about ranges. There will be a link to all of these talks in the slides. First, if you want to learn anything about or everything about ranges, basically any talk by Eric Niebler is where you want to go to. He's the author of the rangify library, and in his talks he explains in depth how ranges work and how you can use them. Then we have a talk from Tristan Brindle on the overview of the standard ranges. And this is your place to start if you want to know what got into the standard library. And also another talk from Tristan Brindle, C++20 ranges in practice. This is a great talk. It's also practice oriented with great examples and very good background information as well. This talk series from Christopher DiBella is also really good. It teaches you how to build your own range adapters, which is what we also know as views. Since the standard library lacks some features currently, you will likely end up using using a third party for ranges if you want to use them, or you going to write your own range adapters. So this talk is really helpful if you want to learn how to do that. And also, if you want to write your own range adapters, I recommend Cybrand's YouTube channel. They have live coding sessions which are uploaded to YouTube, and they show you how to implement views like stride or transform, maybe chunk by, enumerate, and so on. So I highly recommend you learn how to do this from Cy as well. And if you cannot use C++20 yet, or the standard library lacks some features for you, you can have a look at these upcoming libraries. The first library to use is the rangify library, which is the most extensive library for ranges support. And it's also the basis of the ranges support in the standard library. If you want to know more about this library, you can watch the talks by Eric Niebler, because he's the author of this library. Next, we have NanoRange. And I guess this might be the second largest range library there is. It provides concept, range-based algorithm, function objects, projections, and more. You can also go to Cybrand's GitHub, which is Tartan Llama, and get the range adapter they implemented in those YouTube videos and live streams. And the next library is Ranges Next, and it provides only a handful range adapters. It provides ranges 2, enumerate, and product, which is the Cartesian product. And last but not least, we have boost ranges, and boost ranges support range-based algorithms, and they also have a few range-based adapters like strided, for example. And these use the pipe syntax as well. An advantage of boost range is that it is C++89 compatible. So now that we've covered some recommendations and libraries, let's dive into the talk. First, what do I mean when I talk about rangifying your code? A lot of people think about the pipe operator when we talk about ranges, but there's actually more. There's also the range-based algorithms. But of course, in this talk, we will focus a lot on the pipe syntax as well. Ranges are algorithms, are loops. We have the tendency to think in loops first because that's what we learned first, and we're doing them the longest, so they are the most natural to us. A change in that already happened on the introduction of algorithms. It even got and still get backlash from people saying that they are harder to read and they don't trust the algorithm when they don't see how it is actually implemented. The same prejudice holds against ranges. The syntax is the most unfamiliar, especially compared to loops. It's way more a functional programming approach where you describe what the code is supposed to do than not how it is doing it. I'm convinced that once you get used to the syntax, reading and writing the code will get easier and easier. The key is also to learn your algorithms so that you know what is actually available to you. Rangify also means using range-based algorithms. You might think there's not a huge change. We can just omit the begin and end. But it gives us the option to better describe the intent rather than the implementation details. And it also limits the noise. And also, we can now use views in these algorithms. So let's say we have a vector of doubles and we want to change the elements of the vector and store the result in a new vector. I think in C++ there are maybe 100 ways of doing that. Like you can solve this by using a loop. You can use an indexed loop. You can use an iterator-based loop or a range-based loop. Or you can use standard libraries transform. Or you can use in C++20 the range-based transform. As you can see, you can now omit the begin and end and just pass in the vector as the first argument. But now with ranges, you could also use copy. And if you use copy, you can use a transform view on the input vector and modify it with the modify function. This is also a possibility. But in this case, I would write something like this. I would again use a transform view with the modify function and then use the ranges2 function to create a vector from the result of the transform. This has the advantage that I can make the output vector const. Please note that the views transform is part of the standard library, but ranges2 is not. So for the last line, I used the rangv3 library. And also, if you see the compiler explorer symbol, like here, that means I have provided a compiler explorer link with all the code, so you can look at it later and play around with it if you want to. So these little examples always seem a little bit over-engineered. And that is why I came up with a little bit more complex examples. I try to show as many different cases as possible. I will start with some small examples that fit on one slide. The first example is finding a maximum number. And this is actually a simplified version of a problem or of a piece of code that we have in our code base. I need to use simplified versions of the code examples that I'm grabbing from our code base because I'm not allowed to share any code from that code base. So I hope you will forgive me for that. So for this function, we have a vector as input, and it's a vector of strings, and these strings are actually numbers, and those numbers are ints. And to find the maximum number, we have a local variable initialized with the minimum of ints. And then we iterate over the numbers vector. We call string to int on the number and find the maximum number. And then we return the max value. There's no need to use a for loop here. We could have used a transform or something like that. So it's just how it was in the current code. So to rangify this, I always look at the loop and try to analyze what the loop is doing. So in this case, I see that the loop is only looping over the numbers and we don't need an index. And what we're doing in the loop body is we are transforming basically the numbers from string to int. So that's what we can do in our ranges approach. So we can use the ranges function max, which returns the maximum number of the passed in range. And we call it on numbers, and we want to transform the numbers by calling string to int on every element of numbers. And we do this by using the transform view. So for all of these examples, I prepared some highlights which are showing which parts of the code of the above example corresponds to the part of the codes of the ranges example. So in this case, the loop over numbers corresponds to calling ranges max on numbers. And again, the max function also corresponds to the ranges max. And string to int is done here in the loop body above. And in the ranges version, it is done in the transform view lambda. The next example is a sliding mean. And in this case, the mean or the window for the mean was 5 elements. And it was hard coded to 5. So I kept it like this. First, we define our output vector, which is the size of the input vector or the input range minus 4. That is because the sliding mean has some, the sliding mean makes the output vector a little bit smaller. And then we have a for loop iterating from 2 to ranges size minus 2, or the input range size minus 2. And off screen, I have a mean function, which sums up all the elements of the passed in range and divided by 5. And I will pass an array to this mean function that is made up of all the 5 elements from my sliding window. And I store the output into the output vector, and then I return the output vector. Please note that I'm not doing any boundary checks here. So normally in production code, I would check that the sizes are okay and that I can do the actual calculation. But in this case, I'm not doing this. Just to keep the example simple and the noise down. So when we want to transform this into the ranges version, we again need to analyze the loop. And here it's not enough to just look at the loop, because if you would look at the loop, you might think that you need to drop the first 2 elements and the last 2 elements of the input range. And we have views for that. We have the drop view, which drops the first elements, and we have drop last, which drops the last elements, and how many you just give to the view. Please note that we have drop in the standard library, but drop last we don't have in the standard library. So if you want to use drop last, you would need a library like rangify. But in this case, we actually don't want to drop the elements, because you can see in the loop body that we are calculating all the elements from the index. So with ranges, we can use a sliding view. which does all the work that we see above, but without but without actually copying the values. It creates a view over the input range with 5 elements. And it slides this view over once every time we dealt with the current view. And then I call transform on the sliding window of 5 elements, and then passing in the mean function. And I'm outputting everything into a vector by calling the ranges2 vector function. So the ranges2 creates a vector with these transformed elements. And again, I highlighted here the corresponding elements. So for the so the loop and the array with the 5 elements is corresponding to the sliding view of the 5 elements. The mean function will be called in the transform, and ranges2 vector will create an output vector which corresponds to manually creating the output vector and then returning it. The next example is subtract mean. So at Rosen we use or we work with matrices and 1D to 3D, and we're using multi-array for those matrices. In this example, we have a matrix and mean values, which are mean values for every column of the matrix. And I want to subtract the mean from every column of the matrix. And I do that by looping over all rows of the matrix, and then essentially looping over the column of the matrix and also the column mean vector, and then subtracting the column mean from the row value. And I can also rangify this. So for the range version, I need to figure out how I want to handle the matrix. So if I look at the loop, I see that I essentially want to loop over every element of the matrix. And in this case, I can actually iterate over the matrix flat. So there's no need to iterate over the rows first and then the columns. To do that, I created a span from the multi-array. The span will create basically a view of the matrix, but flat. So all the elements are flat. So this is 1D. And I call the ranges transform function on this because now I cannot use the transform view, because the transform view only accepts one input and it will only transform the range on the left side of the pipe operator. But the ranges transform accepts 2 input ranges. So this is why I'm using ranges transform here. So the first element is the span that I created from my matrix. And so if I wouldn't use multi-array, if I would use another container, I could probably use the join view. The join view makes a 2D matrix 1D and a 3D matrix 2D and so on. But since this is multi-array and it has some implementation details that prevents that, I cannot use the join function or the join view. So I'm creating a span which does basically the same thing. Also, a span doesn't copy the values, it just creates like a view to those values. So it's perfectly fine to use a span here. And the second input range for the transform function is the column mean. And I cannot use the column mean as is because it is only the amount of elements of one column of the matrix. but I want to iterate over every element of the matrix. So I'm fixing that by using the cycle view. And the cycle view, what the cycle view does is it takes the vector, and if you're at the end of the vector, it will start at the beginning again. So it will cycle around the vector every time. Then I need to say where I want to store my output. I want to store it in the matrix. And then the last element for the ranges transform is a lambda. And this lambda has two inputs from both of those ranges. The first input is the matrix element, and the second input is the mean. And then I return the matrix element minus mean. And the corresponding code lines here are for the nested loop over the matrix. I use ranges transform and create a span from the matrix to get like a flat view. And then I need the column mean, the correct column mean, and I'm going to use a cycle view for that, so that the column mean vector is repeated over and over again until we reach the end of the matrix. And the calculation of the matrix element minus mean is done in the lambda for the transform. Yeah, so this is how I would do this using ranges. So the last of the small examples is the arange function. And you may already know this function from Python because it's essentially the same thing. It creates a range with the size of len and the start value start that you pass into the function, and it counts up the step value. And in this case, again, I want to have a vector. I initialize the vector with len and start. Then I iterate over, then I iterate from 0 to len. And in this case, I actually need the index. So I'm going to add I times step to the output vector, which creates the range that I actually want. And then I return the output. So to rangify this, I again have to look at the loop and see what the loop does. And in this case, I actually need the index from the loop. I can do this by using enumerate, and enumerate gives you the index to a corresponding range. So the corresponding range at this point, I don't really have. Corresponding range would be the output vector. I could make the output vector the same way as I did in the above version here, but I'm not going to do this. I'm using repeat n for this. Repeat n is also a view, and it repeats the value that you're passing in len times. So the start value will be repeated len times, which will create the same thing as the initialization of the output vector, but it will do it on the fly because ranges are lazy. So the repeat n will repeat the start value, and enumerate will give you the index to that value. And then we call transform on the result of enumerate. And transform gets passed in a function called next value that gets passed in the step. And we want to output everything into a vector. So now let's look at the next value function. It is a function that returns a lambda. And the input of this lambda is the index and the value, which is the result of the enumerate function. And if you're using views, what you're getting here is a tuple. So you can deconstruct a tuple into the index and value, and then calculate what you want to calculate. So here I want to add index times step to the start value. So the corresponding code lines here are the for loop and the enumerate function. And the initialization of the output vector can be done by repeat n. And then I'm using transform and the lambda above to calculate the next value, which corresponds to the loop body. And then to output the result, it is the same as creating the result and then return it. So these were the more simple examples. But I also prepared a more complex example, and this will actually be the last part of the talk. So first I'm going to explain what the complex example is. Then we will implement this in a C++17 way, how I would implement it in C++17, and then we move over to rangify this. So what I want to implement is the so-called HONT method, also known as Jefferson method or greatest divisor method. And this is a method that you can use for allocating seats in parliaments or proportional representation systems. And I'm going to show on this example how it works. So in this example, I have 3 parties. And party 1 won 110 votes, party 2 won 85 votes, and party 3 won 35 votes. And I have 7 seats to allocate. So this method will, so in this method, we will need to count up from 1 to the number of seats that we have, and then divide the votes by these numbers that we just created. So we begin with 1, so we divide 110 by 1, which is 110. Then we divide it by 2, then we get 55, and so on. We do this for all these divisors for party 1. And we do the same for party 2 and for party 3. Now the next step is to sort these the results of the division. So the biggest number is the 110, then we have 85, then we have 55, and so on. And we only have to do this until we filled up all of our seats. And the last part of the algorithm is to count how many seats the party won. So party 1 won 3 seats, party 2 won also 3 seats, and party 3 won 1 seat. So this is the entire algorithm. And as I said, I first want to implement this in C++17. So first I'm going to create a method for this, and I'm deciding on the input. And for this, I want to have a map as input, and the map holds a string and an int. The string represents the party and the int the number of votes. And then I also need the total number of seats. This is all the input that I need for my function. So the first step is to calculate those quotients here. So what we need to do is first decide on the output that we want to have from this calculation. And here I decided that I want to have a vector of pairs, and this pair holds a string which holds the party, and a double which holds the result of the division. There's no need to use a pair. I could also use a map or a struct, so there's no need to use a pair, but I just used it here. And then I have a for loop starting at 1, counting up to a total number of seats plus 1. These are the seat divisors. So and next I'm going to iterate over every element of the map. And I'm directly going to deconstruct the map so that I have the party and the number of votes deconstructed. And to calculate the proportional votes, I will get the number of votes per party and divide it by I, which is the seat divisor. And I'm going to store everything in the vector of pairs. Normally, I would reserve a size for the proportional votes, but I just didn't do it here to save some space. Next, we need to sort this, or we need to sort the result. To sort the result, I'm going to use standard sort on the proportional votes vector. And because the vector holds a pair, I need to tell the sort function which elements I want to be sorted, which I want to be sorted the vector on. And here I want to sort the vector on the second element, which is the quotient, which is the result of the division. And then I'm going to resize everything to the number of seats, because that is really all what we need. Next, I'm going to count how many seats which party won. And I'm going to do that by using the, first I'm going to decide on a output for the function, for the overall function, and I decided to use a map as well with a string for the party and int for the number of seats. And now I need again to iterate over the input map, but this time I really only need the party and not the number of votes anymore. But I still deconstruct everything to get those two variables separately. And then I use the countif function on the proportional votes vector to count how many times the party is in the proportional votes vector. And this is stored in a pair. The party is stored in a pair, and it's the first value of the pair. And once I have this, I'm going to insert the party and the count into the output map, and then I return the output map. So this is the entire method. If I change the font size a little bit, it actually fits on the slide. If I would implement this into our production code, I would make this into 3 functions, because this is clearly 3 different blocks. So the first block is to calculate the proportional votes. The second block is sort and cut. And the last block is to count the seats per party. And now that we're moving on with rangifying this code, I will focus on these 3 blocks individually. I'm also using rangify to rangify this, because I'm using a lot of features that are not in the standard yet. So again, with this, the hardest part is to know which algorithms you can use, and then in the end, how to use them. But I guess that's probably true for all new skills. Here again, we're going to look at the for loops. So the first for loop creates these divisors where we have to divide the number of votes by. And we can do this by making an integer sequence by calling use ints, which will create this sequence for us, starting by 1 and ending by total number of seats plus 1, because the end value here is also exclusive, like it is in the for loop above. Next, we have a look at the nested for loop. So what this nested for loop is actually doing is it is combining all the elements of those seed divisors with all the elements of the map. And we can actually combine all elements of one range with all elements of another range by calling Cartesian product. And Cartesian product will do exactly that. So this is how it looks like. This is the first element of the result of calling Cartesian product. It holds the first element of the map and the first element of the seed divisors. And then the next element is the second element of the map and still the first element of the seed divisors, and then the third element of the map and the first element of the seed divisors. And if we are going on, then we will repeat the elements of the map, but now we get the next seed divisors, and so on and so on. So as you can see, this will create a huge range, or a huge view actually, of all elements of one range combined with all elements of the other range. And this is a new range, or a new range view. And we can now transform this new range that we got and calculate what we want to calculate with it. And in this case here, I created a lambda to calculate those quotients. And the lambda takes the votes and the divisors as input. This is the result of the Cartesian product function. And I like to deconstruct my tuples. So what I get back from the ranges library in those cases is a tuple, and I like to deconstruct it. And now I get party and vote, which is the pair from the map, and I get the divisor. And now I'm going to return a new struct that I created. In the C++17 version, I've used a pair, but for the C++20 version, I decided that I wanted to use a struct. And I'm going to show you why in the next block of code. But for now, it is doing just the same as the pair is doing. So the first element of the struct holds the party name, and the second element holds the quotient. And I want to store everything in a vector. So like I did with the other examples, I want to show you which elements of the one example corresponds to the elements of the other example, or of the other version. So the first loop corresponds to creating an inst view. The nested loop corresponds to the Cartesian product of both ranges. The transform view corresponds to what we do in the nested loop body. And I also created a lambda for this because I also think it's more readable if the functions that you're calling have good names. And so this lambda tells you what it is doing. So if you just read the transform line, I guess you can figure out what the function is doing without looking at the internals of the function. So that's the goal, actually. With the example above, you have no way of knowing what this is doing. You have to analyze the code. You have to read the code line and figure out what it is doing. So that's why I like to make lambdas for the transforms, because I then can give it a good name, and it should be readable by just the name. And the output I'm going to create in the C++20 version with ranges to vector, and for the C++17 version I created a vector separately outside of the loop. So again, as you can see in the C++17 version, it describes more how it is done, and in the C++20 version, it describes what is done to the code or in the code. This may be harder to read in the beginning, but I think you can get used to it, actually. So next is the next part of the function, which is sort and cut. So now we want to sort the proportional votes in descending order by the quotient value. In C++20, I can now use the range sort algorithm, and I can omit the begin and end on the proportional votes. And I actually think this may not look like a big change, but I think it limits the noise. I actually think it looks better. And for now, I have the same lambda, and I will cut the vector down to number of seeds. But next, I need to change the lambda body, because I'm not using a pair anymore. I'm using a struct, and the struct actually has names, or the struct field actually have names. So in this case, I changed second to proportion, but I can have this in a simpler way. And I really like this feature in C++20. You can now use a so-called projection. And what it does is that you can now use the standard greater function, because in this case, we want to sort in descending order. And then you can give a third argument to the function, which is called a projection. And it is actually a member to the a pointer to the member of the struct, and of the struct member that you want the sort to be applied to, or the greater function to be applied to. And I really, really like this syntax, because I think it reads so nicely. You know exactly what it is doing. You want to sort proportional votes in descending order, and you want to sort it by proportion. So I really, really like this. So this would be the C++ 20 way if you're using the standard library. But you can also use rangify for this, and rangify has a nice little syntax for this as well. And this is the pipe equals operator. And what the pipe equals operator does, it applies the function to the vector on the left side of the pipe equals operator. And in this case, sort isn't a view anymore, so everything we saw from rangify until now was a view. But a sort isn't a view. A sort is an action, and an action will be performed eagerly, that means right away, while views will be performed lazily. And this sort function, you can give the same arguments. You can give it the standard greater function, and then a projection to your to the member of the struct that you want to apply the greater to. I have no preference actually in using like the C++20 way, the standard library way, or the rangify way. I like both versions here. And for now, I'm going to omit the resizing of the vector, and I'm going to show you a little bit later why I did that. So next we're going to the last part of the function. And I guess this might be the hardest to understand when done with ranges. So when we look at the loop here, at the first loop, we are again looping over the input map, and we deconstruct it into the party and the number of votes. but we don't need the number of votes anymore. We only need the party. And in C++20, you can use the keys view to only get the keys from the map. There's also a corresponding values view if you want to have the values from the map. But this is essentially what the first loop is doing. It gets all the party names. And now I need this countIf. And I'm going to do that by calling transform on the keys. And I have written a function here that needs the proportional votes and the total number of seats as input. And I'm going to show you in a second what this function here is doing. And I defined the output to be a map. And ranges2 is really great. You don't have to make a vector like I did here in all the examples. You can also make a map. And this is what I'm doing here. So I think what is maybe a little bit harder to understand is that in this case, you are performing everything on the input map and only on the keys of the input map. And this is actually enough to do all the calculations. So let's look at the count seats per party function. Again, I tried to choose a good name here so that if you only look at this part of the code, you kind of know what the code is doing without looking into the function and into the details. So count seats per party is returning a lambda and needs as input the proportional votes vector and the total number of seats. And what it does, it calculates the number of seats. This is an extra function, and it will return a pair of the party, and the party we get from the keys view and the calculated numbers. And now we need to look at the calculate number of seats function. And this needs the proportional votes as input, total number of seats, and the party name. And like in the C++17 version, I use countIf, but in this case, I'm going to use the ranges version of countIf, the range-based version. And the input argument or the input range for countIf is the proportional votes. And I'm only going to take total number of seats elements. So take view only gives you the number of elements that you pass in here as a number. That's why I didn't cut the proportional votes vector. I could have done this. It actually makes no difference, I think. So in this case, resizing is no problem at all. But I also really wanted to use the take view. So that's why I did it this way. And countIf again needs a lambda, and this lambda here has the argument of the proportional votes, which is the struct. And in this case, I'm not going to deconstruct the struct. I could do it, but I only need the party, and I'm comparing the party to the party that I get from the input keys. So this is a little bit nested. This is maybe a little bit harder to understand. But it is doing exactly what the function name is telling you. So now when we look at the entire function without the external lambdas and functions, this is the entire algorithm. And I actually think that you can read this really nicely. So we first create the seat divisors, which is an ints view, a view of ints of the numbers 1 to number of seats plus 1. And then I'm going to calculate the proportional votes by creating a Cartesian product from of votes per party, which is my input map, and the seat divisors. So now I have like this combined range of every value from this one range and value of the other range. And then I'm going to transform this new view by calling a function that is called divide votes by seed divisors. And I don't need to look into this function to know what the function is doing. And in the end, I want a vector. So when I read this, I would understand what these 3 lines of code is doing. And the next line would be to sort the proportional votes by using the rangify sort. And I want to sort in descending order. That's what I'm reading from greater. And I want to sort by proportion. And lastly, for the output, I want all the keys of the input map. And I'm going to transform them by counting the seeds per party, probably on the proportional votes vector, because this is what we calculated before. And I need the number of seeds as input. Maybe it would also be very clear if I would resize the proportional votes here and don't use them, then don't use the number of seeds then as input for the transform. That actually may be a little bit clearer. I don't know. And then in the end, I'm going to create a map from the output. The only thing I'm not seeing here is the order of the elements of the map. But I'm guessing that it would look the same as the input map. So the party first and then the amount of seeds second. So this is how I would do this in the C++20 way. So to sum everything up, there are a lot of great talks about ranges out there, and there are also many libraries that you can use if you want to use ranges but cannot use the standard library yet, or the standard library does not have enough features for your use case. Not every range-based code needs to use the pipe syntax. You can also use the range-based algorithms, which I think are a very, very nice addition to the standard library. The key to rangify the code is to know the available algorithms, and there's no way around it. You're going to have to learn your algorithms. You're going to have to learn what is available to you. But I'm really convinced that once you get used to this and once you know your algorithms, it actually gets simpler. And for the method of finding the right ranges to use in your code, I think it's best to analyze the loops and try to figure out what the loop is doing and what is done in the loop body, and then find an algorithm that describes what this loop is doing. And a surprising number of times you will find a matching algorithm or range for that. In my company, we are using a combination of standard ranges and self-written range adapters, since the standard library lacks a lot of features and we have a hard time incorporating some other libraries for us. So we implement what we need when we need it. But also the standard library provides a great framework to write your own views. And also we are free to use ranges in new code and also in existing code when we refactor it, which I actually think is really nice. So I'm always learning the new features right away because I'm not just allowed to use them, I'm encouraged to use them. Thank you very much for your attention. Please let me know if you have any questions.